and back here. So what else? Well, metals lose electrons. They become positive ions. These guys over here gain electrons. Okay, gain electrons. They become negative charged. All right. The idea that they hold on to electrons, metals hold on to electrons loosely and nonmetals tightly, creates these other properties that you probably well know of metals. Other things of metals. Okay, there's something called luster. So the fifth thing that they have is they shine very easily. They can polish very easily. So number 5, I would draw, is they have something called luster. Luster means shine. And if you think with me, if you take electrons of metals, and if they're held loosely, and you brush them in a certain direction, you can actually smear an atom, electrons, over a large area, and that creates that mirror edge shine. Okay, nonmetals do not have luster. Okay, they don't shine so easily. I mean, there certainly are some examples of compounds and composites that will shine that are nonmetals, but generally speaking, they don't. Okay, metals are very dense and they're very hard, usually, whereas nonmetals, okay, are brittle. Think with me for a second why these would be brittle. If you're holding on to electrons tightly between bonds, okay, and I'll draw that scenario right here, okay, you would think, so here's a nonmetal bonded with electrons to a nonmetal, and by the way, that bonding would be covalent sharing, and there's no other things going on besides competition for these electrons because they're both forced to share, they're both attracting tightly. If you give this a good force, it's going to break right here. And it's going to cleave right in this position where they're sharing electrons in a very local area. Okay? So my friends in chemistry, they are brittle. They break. They crack. Think of ceramics. Think of pottery. They crack. Whereas metals do not. In fact, metals are so hard and they don't break so easily. Now, there certainly are metals that go against the grain and can break, and there's always exceptions to all these rules. But metals don't break so easily because their electrons are shared loosely in the compounds. They're able to move and be held loosely. There's bonds between metals, but these bonds are in all directions. And that's what gives the elements, the metals, the ability to be shaped in any direction. So metals can take on any shape. And that property of taking on any shape when you heat it has 2 words. It's called ductile and malleable. Okay? So ductility and malleability is the property that you'll hear with metals. Ductility, now really that means being drawn into a wire, a thin wire, and malleable. Malleable. Okay? These guys can be heated and shaped into any shape because of their electrons loosely held that can move throughout the compound. Whereas nonmetals have that localized bonding only in one area, are brittle. And those are the major, okay, properties that you're responsible for knowing, and they all stem from the radius. Now the transitional metals, they have some extra properties. They have all the ones here of the metals. They're the metals you think of mostly. They're special in that, number 1, they have multiple oxidation states. As we learned in some classes, okay, they all at least have one oxidation state, but they mostly have multiple, meaning they can be +2, +1. Some places, some of them have 6 different. They're all positive. So you have more than one charge. You notice the alkali metals can only become +1. The alkaline earth metals can only become +2. They only have one choice. These guys have multiple oxidation states that are positive. Okay, I know that these guys have multiple positives. These guys, if you look to the right, the nonmetals, do have some multiple positives too. We'll get into that in another unit. But their top number is negative. So we're not dealing with the other ones there. 2, most important, these guys form colored solution. I can't give you the full story why yet, but transitional metals, when they make solutions, are colored. All other metals that are not, when they make solutions, make clear solutions. For instance, your blood is red or reddish, dark red maroon because of the iron in the red blood cells, in the hemoglobin. Okay, copper has a very classic greenish blue color solution that I've actually shown you. Okay, so the solutions that are colored are due to transitional metals, and it's due to something called the crystal field splitting of the D sublevels. Beyond the scope of this course, but I do talk about it in AP. But that's something you have to be aware of. Okay, so those are the basics. Now we have some other things to talk about. All right, and let's go to the other periodic table because I'm running out of space, but I can do that here. Okay, now I'll go to the other one. There are another periodic table on here somewhere. Let me pause and. Okay, so back to my periodic table, and you could use the same one. I'm just trying to clean up some mess here. So this is hydrogen, helium. This would be radon. Okay, this would be fluorine. This would be chlorine. This would be bromine, iodine. We have NOF here. Those are the ones I kind of want to show you. Okay, so what am I showing you here, my friends in chemistry, is where the actual different phases occur. Okay, now if you think with me for a second. Okay, so what we're going to do now is we're going to talk about the different phases of the periodic table. All the atoms given to you are at STP, standard temperature and pressure. Some are liquids, some are gases, and most are solids. How do you remember them? Very simple. Okay, I call this the backward LL rule. Okay, nothing earth-shattering here. I take my first backwards L. Okay, I'm going to draw a little L here, part of the L. I'm going to add some color, okay, to this. All right, I'm going to make some transparency because I'm that kind of a guy. Maybe. And that didn't really work, did it? Okay, let's try that again. So we'll take this top, all right, here, and we'll take another triangle down here, and this L backwards falling on its side, okay, represents all of the gases. All right, so if I was to fill this in with this, I don't know why it's not working, but you get the idea probably. Let's just go to a thick shape here, yellow brush, highlighter. Let's go here and fill this in and this in. This represents all of my gases in the periodic table. So let's go back to my other table since I think that works out better. So back to my other periodic table. This would be 1L, okay, backwards L. It's an LL rule, and Nafkal right here. So if I was to go back to my red colors, okay, or whatever color this is, NOF, all the gases in the periodic table are helium, I'm sorry, this is hydrogen, to helium, down through radon, and nitrogen, oxygen, fluorine, chlorine. Easy stuff. The liquids, and there's only two, okay, there's bromine, and there is mercury, okay, which is actually right here. Let's draw that guy in. Mercury, all right, Hg, and those are the two liquids. This is a liquid metal, this is a liquid nonmetal, and of course, everybody else is a solid. If you look very carefully, you've got halogens are the only group that has three phases of matter. It's got two what? Gases, one liquid, and one solid. Okay? Whereas the others have different phases. Interesting enough, we talk about chemical reactivity. Okay, what happens to the metallic reactivity as I go down a group? As I go down a group, what happens to the metallic character? This is the metallic character that we talked about. What happens to that as I go down a group? Well, because it gets bigger, okay, there it is, they lose electrons more easily. So you get more metallic as you go down. So the metallic reactivity increases. Now look over here. It's the land of nonmetals, the smalls. Well, as you go down, guess what? these elements act more like metals. You would say iodine is more metallic than fluorine. Even though iodine's a nonmetal, look at that. It's a solid. It's bigger. It acts more like a metal. Look over here. These two, if you check out your reference table, have positive oxidation states. Chromium and xenon actually lose electrons. Now, they lose it only to fluorine, but they do lose it. Why? Well, because they actually become almost as big as some of the metals. All right? Now, something else to think about. Over here, of all my alkali metals, who is the most nonmetallic? And you would say lithium. Even lithium is a metal and it's pretty big. It's smaller. So as you go across the periodic table, the metallic reactivity decreases and the nonmetallic reactivity increases. So I can answer those questions. Look at group 15 for a second. Who is more metallic? The nitrogen end of the group or the bismuth end of the group? Okay. Well, if you look, these guys are nonmetals, and as you move down the periodic table, look at this group. You have nonmetals, you have nitrogen, you have phosphorus, you have arsenic. Oh, it's AS there. Okay. Wait a minute. These two are nonmetals. This becomes two metalloids and eventually become a metal. So this actually shows that this group has a change of metals to nonmetals. So the metallic properties increase. So I can ask you questions about the reactivity of elements. Now, if I just say reactivity and I bring you in this area, what happens? Who is the more reactive element? Fluorine, chlorine, bromide, or iodine? By just saying reactivity, because you're in the nonmetal area, how do nonmetals react? By gaining electrons. So who's best at that? Fluorine. If I say who's the most reactive in this area, you would say theoretically fluorine's the biggest. It will lose the best. But if I say who is the most nonmetallic in the alkaline earth, you would say beryllium. It's the smallest. Metallic properties increase as you go across and down. As you get bigger, gosh, we just can't get away from this, can we? So we become more like metals this way and down, and more like what? Nonmetals across and up. All right, I've said enough. I have some questions I'd like you to do after this, and I'll see you Monday.